Welcome to Rational Science. Once again, we're here every Sunday talking about physics. We're the only site that does physics out there. Everybody else does mathematics. They move concepts around. We move objects, things. Today we're going to talk about distance, location, okay? Some people might think it's a boring subject, but I don't know. I like it. I think it's a good subject. I'm going to start with a comment someone made related to extinction. I'll just address that real quickly. Says, I would like to hear your opinion on some of the stuff going on in our world right now. Donald Trump swears he can stop wars because he is friends with the leaders of other nations. Can Trump actually do anything in 4 years? Is Trump actually going to make a difference? I've never been a fan of politics. I can't say I've never been, but I was when I was young, but that's been a long time. You know, I stopped paying attention to politics a long time ago. In fact, I'm a citizen of two countries, and I don't vote in either one if I can help it. So, I don't give my vote to anyone. What can I tell you? I'm not an astrologer. I can't tell you what's going to happen in the next 4 years. The way I look at it is, I look at politics and economics only in relation to extinction. I'm saying that our humanity, our species, is about to become extinct. About to become means, in a short time. Exactly when, I can't tell you. Is it going to be 4 years? Is it going to be in 10 years, in 20 years? I can't tell you. I can only tell you the circumstances. That's what I look at. And the circumstances are that the global economy is going to collapse. Why is it going to collapse? Well, just in general terms, the United States is the biggest empire that ever was and that ever will be. There will not be another empire after the United States. A lot of people say, well, if the United States goes down, China comes up, or Russia, or maybe some kind of collusion between the two of them. No, history will not repeat itself in this instant. We're at the end of the line, and there's a lot of reason behind that. Okay, among them that we're at the last stage of economics, which is the service stage. We're all service providers today. We stopped doing hunter-gathering, we stopped doing agriculture, we stopped doing manufacturing. Most of the economy of the world is going further into services. And you can't run a world economy on services. Services is another word for unemployment. Anyone who's into services is unemployed. Okay, that's the way I look at it. When you're looking at the earth from up there, all you see is what we constructed. You don't see the services. Services are promises. Anyways, I think the United States will not allow, China to advance militarily, especially beyond it. And there's going to be a war. The incident's going to happen. The militaries of both sides will ensure something like that happens. And when that happens, it's only going to make the economic situation a lot worse. And we can't recover from a world war, whether we use nukes or not, which I think we will, but we can't recover from that because once we have a war, the whole economy, forget about the people who died in the war, but the whole economy of the world will be shot. So the way I look at it, politics, economics, only in relation to extinction. That's the only thing I look at, and I don't do politics anymore. Now, I'm an easy pushover, very easy pushover. I'll vote if they give me a keg of beer or a six-pack. Then I'll vote for that, and I'll be honest, I will vote for that guy. But they have to give me something. I'm not going to give them money and also give them my vote. I'm not crazy. Voting is not a right. Voting is not even a privilege. Voting is whim. It's like you ask an actress in Hollywood for her autograph, right? For her, it's whim. She wants to give it to you or not. For you, it's a privilege. There's no right. No rights involved either way. And voting is the same thing. The politician, he comes and begs for your vote. For him, it's a privilege. for it to receive your vote. For you, it's whim. If you want to vote for him, you vote for him. You know, rights play no part either way. So, yeah, if they want my vote, for me, it's not a right, it's whim. And if they want my whim, they're going to have to give me something. And a keg of beer would do it, okay? Anyways, that's what I have to say about that. About politics, I don't care about politics anymore. Don't get involved with that. A lot of betrayals in politics, so I'm out of that. Don't care about it. Let's move on to the subject matter today, but I'm going to give an introduction here. It's related to last week. We talked about, you know, that we need objects to do physics, and so we need to put physics in the proper context, okay? And here it is. Okay, this was what I put out there. Science equals rational explanations. That's what science is. Science is not descriptions, like in mathematical physics. They describe something mathematically and they call it a theory. No, a theory is an explanation, not a description. And an explanation is not a bunch of descriptions either. You know, you need to have causes, and descriptions don't give you causes. So yeah, physics, we don't do philosophy here, but there's the definition, the way we look at it. Rational explanations of reasons and purposes. It's about behavior, why people do stuff. We don't do that, you know, that's for psychology, historians, etc. You know, major people who major in those subjects. We do physics, and physics is rational explanations of causes and mechanisms. Okay, so that's our starting point. And so now we know what physics is according to this site. You don't have to agree. A couple of people don't agree, and they say, when you say we do, when we say we, when you say we, do you mean Bill and Hans? That's my son, my younger son. I don't recall anyone else doing physics your way. Okay? Another fellow says, you're barking at the wrong tree. You need to stop focusing on what physics should be. It is what it is, always been math. You would like physics to explain, but that's not what it does, right? Physicists don't care about the why. And they're not physicists, they're mathematicians who call themselves physicists. You're going to need to come up with your own science, answer the why. Call it Gades. Yeah, the issue here is, you know, we don't care how many people in the world vote for a definition. Definition is something you defend, not something you vote for, not something you look up in the dictionary, not something that you do because of tradition or because, you know, authority, that's what they taught you or that's what you learned, etc. None of that has anything to do with science. In science, you have to defend your definition. You have to get your shield, your sword, and fight. Get in that ring and fight. And so, yeah, all I can tell you is people say, well, you know, explanations, physical interpretations are not part of science. That's what they say. Well, you know, people then ask, you know, why does this pencil fall to the floor? Why does it fall downward? Why does it fall to the ceiling? And no one in the last 10,000 years can answer that question. And that's the type of question people ask, because people don't, the common man, the layman, they don't care about math, equations, calculus. They're far away from that. They say, well, why does a spoon fall to the floor? Please explain. These people cannot explain. They say space-time is warped. What do you mean space-time is warped? Space-time is a concept. Yeah, we don't understand it either, and that's philosophy anyways. So two things. Why did they try to answer that question? Why did we go to the physicists, so-called physicists, to try to get an answer to that question? If that's not part of physics. Second, who does? Who should I go to, if not a physicist, to tell me why the pen falls to the floor, if not a physicist? Who handles that subject matter, if not a physicist? And yeah, these people will tell you that they don't do that kind of work, but then they do try to do it. They try to give you an explanation. Why? I mean, don't give me an explanation. Just stick to your math, your equations, and we're done, right? Why are they trying to give you a physical interpretation? And so those are the questions you have to ask yourself. And then you do have people like I showed James Beecham And he says, yeah, that physicists want to know why. They do want to know why, just like anybody else. But they don't know why, and so they give you these irrational explanations that space-time is warped. So, you know, it's up to you to figure out, and every man's up for himself. You can't just go out there and say, well, this is what all the physicists say, or what the mathematicians say. We don't care if all of them gang together and form the Flat Earth Society. Does that make it real? You know, so every man's for himself. You got to reach your own conclusion by yourself. Okay, so what did we say? Here we have it. Foundations of physics, right? This is what's the base of this discipline, okay? Golden principle of physics, you can't do physics without an object. You need an object. If we have no things in the universe, no object, no atoms, no gases, no planets, no nothing, right? What's happening? What's taking place? What physics is happening? What would there be to explain? What experiments would you run, assuming the experiments are part of the scientific method, right? I mean, what's happening if there's nothing there? So the first thing you need is objects. You need to put objects in there. And so the first definition we need in physics is the word object. You need to know what an object is. An object, that which has shape. There you have a shape, black one. I hope you see it. It's got shape. We don't know what it is, but that's an object. Call it X if you want. Okay, no problem whatsoever. Okay, so we know what an object is. It's that which has shape. Okay. Now, a fellow said, or the other day, made me laugh, says, no 3D object has shape. No 3D object has shape. It has form. Well, I told them that in other languages, there's no word for shape. I know at least 2 languages that don't have it. One is Spanish, the other one is German. They don't have a word for shape. It's always form. Everybody uses form in those countries. So there is no word for shape. Shape, everybody identifies with 2D and form with 3D. In physics, we call it shape or form are synonyms. But even if we were to go with this fellow's objection, every object, 3D, right? Every 3D object has shape because shape is a 2D property by definition or according to the way they see it. And every 3D object includes 2D surface, face, or whatever. So all forms include shapes. And by using the word shape, we cover all objects in the universe, whether they're 2D or 3D. So shape is the correct word, okay, in English, right? In other languages, we use the word form. Okay, anyways, fellow says that action forms objects. He says that objects are made of motion. And that's one of the things we're going to look at today. No, it ain't. First, you have to have an object before you have motion. You have to define the word object before you define the word motion, action, or change of position, or whatever you want to call it. You need objects to do motion. And they want to do it in reverse. They say motion builds objects. Objects are built of motion. No, absolutely not. But this is what they have in the back of their minds. And so he says an object is an obstruction that was thrown in your way. An object would mean an entity which is thrown in the way of another. In other words, see touch, primarily touch he's referring to here. You need touch. And no, because now you have 2 entities. You need 2 entities to define object and entity. So it's an irrational notion what this fellow proposes. He can't defend that under any circumstances. The see-touch criteria are both irrational, both see and touch, because you need a second object to do the seeing or the touching. And you need an experiment. You need the experiment of seeing and touching. Is the asteroid an object before it touches the moon? Hopefully before any entity touches or sees something else, it's already an entity. And so you need to define entity before the see and touch, before they do see and touch. So because of this fellow's definition, he ends up with nonsense like, that water and air are not things, okay? Motion is a property of matter. It needs motion to maintain form. Absolutely not. Form is a static concept. We see it in a single frame. We don't need to see motion in order to have form. Okay, we're not talking about forming something. We're saying that whatever has form, whatever has shape, static concept, we see it in a single picture. And there you see it. He comes up with the notion that water doesn't have shape. And that's why, because they have this notion in the back of their minds that water is malleable. It changes shape from second to second, from frame to frame. Yeah, changes. So does gas, right? So we have all these, objects. You have like table. Table doesn't change its shape immediately, even though every atom in there is moving. But he didn't realize that. Every atom in your table is moving. The electrons are moving. Everything is vibrating in there. We don't see it every day, but your table is moving. Okay, it doesn't move like from here to the other side of the room, but every atom in there is moving. So you're not touching a static thing when you touch a table. It's already in motion. All the atoms are moving, vibrating in there. They're doing their jiggle, right? But irrespective of that, the question here is the following. If we take a snapshot of the table, if we take a snapshot of water, if we take a snapshot of air, if it's color-coded, you take a snapshot, you would see a blob. You would see a shape, a form there in front of your eyes. And there you see it. Here you have the astronaut pops the balloon. You had a red balloon there. And it's water. Air, you want air? No problem. Air or water wouldn't matter. You have a blob of atoms coming out. You take a snapshot at a given point, and there it is. There's your snapshot of water, right? And does that thing have shape? And it's not a question of what is the shape of. No, the question is a yes or no type of question. Does it have shape? The answer there hopefully is yes. Water does have shape, so he is absolutely wrong that water doesn't have shape. Yeah, water has shape and doesn't need a container, because this one is down in outer space without a container. So yeah, you can put water in a balloon, you can put water in a container, and it has the shape of a container, right? But you can have water or air out there in the middle of space, and it'll be a blob, which gradually disperses probably. We don't care. We just say we take a snapshot at a certain point in time, and that's a photograph. You have a picture, a still image, and that thing there in front of your eyes has shape, period. And if it has shape, it qualifies as an object. Okay? Very simple stuff, really baby stuff. Okay, there shouldn't be any argument about these things. Okay, one person who also believed, because of faulty definitions, right, was who believed that water and air and all that kind of fluids are not objects, was Ayn Rand. And people sometimes say, Bill, you said the same thing as Ayn Rand. I call it ain't for Ain't Rand, because she didn't have it right. She never got it right. She didn't know what an object was, what she called an entity. She did not know what exist means. So she failed the two key words of physics. And people say, well, she wasn't a physicist, she was a philosopher. No, she was not even a philosopher. A philosopher is someone who explains behavior, right? Reasons and purposes. And when Ayn Rand was a religious fanatic, she did politics. And politicians, people who do politics, are religious fanatics. Okay, that's what it is. It's opinion, it's recommendations how you should live. That's religion. That's got nothing to do with science. Okay, and you can see Ayn Rand just put everything related to perceptions and senses everywhere. You see the word perception everywhere there, and she says, an entity is a solid thing with a definite boundary, as against a fluid such as air. Air is not an entity. Fluids are not entities. And she said up at the top, an entity is a thing. Right, so she's saying that water is not a thing. She says air is not a thing. Fluids are not a thing. And that it just gives you an idea that she had no notion of what an object is, what a thing is. She had the same notion that everybody else had. Among them, these two gentlemen, they preceded her. Let's see. Give me a second here. I lost this file. These two gentlemen. There we go. Hume and Kant, okay, David Hume. And he says, he already said this in the 18th century, both of them really. Said the idea of existence is the very same with the idea of perception or object. Okay, so he's saying existence is object, things are existence, are existing. In other words, he saw no difference between the word exist and object. And at the bottom, he says the idea, when conjoined with the idea of an object, makes no addition to it. Whatever we conceive to be existent. Absolutely not. And Immanuel Kant, who came a little later, said more or less the same thing. By whatever and however many predicates I may think a thing is, nothing is really added to it if I add that the thing exists. And they were both obviously completely wrong. Yeah, and part of it is that they confused, like Ayn Rand here. Let me put her back. See at the bottom, she believed that exist and entity are the same, are synonyms, that they are the same things. Something exists which one perceives, and that's what she called an entity, something that perceive, whatever you perceive. So they don't see a difference between existence and perception, and between existence and an object, because they define both of them in the same way. And so we need to clarify that difference. No, exist is not the same thing as object. These are two different words. They mean something totally different. Exist means object that has location, and object is simply that which has shape. So in order for the object to exist, it must, in addition, which Hume and Kant couldn't figure out, neither could Ayn Rand. None of them could figure out that the difference is location. You need to have location. Here's a good old God. Okay, I hope all of you met him. That's God there. And that's an object. That's a thing. That's the only thing in the universe at that moment in time. You don't see anything else there. Okay, so God is flying around. He's the only object. And you can see he's not flying around really, because we took a snapshot of him. And so we can point to this thing, call it God. And so now you know what God is. And does God exist? Well, God doesn't exist yet, because God does not have location. In order for God to exist, this is what he's got to have. He's got to have distance with respect to every atom in the universe. Only then does God exist by definition, not because we believe or stop believing or don't know if to believe or not, or whatever answer people give related to belief and knowledge. No, God exists if God has location, and they have all the atoms in the universe. There's distance with respect to God from every atom in the universe. Now God exists. Okay, by definition, because that is the definition of exist, the scientific definition, the one we use in physics. Okay, so if God wants to exist, very easy. Just have location, and you can say, let us assume God exists. What did you say? Well, you said, let us assume God is an object first. Can't be a concept like love or intelligence. And God has distance with respect to everything that exists, everything that has location, every atom in the universe. Then God exists, by definition. So that's what you said when you say, let us assume God exists. Okay, so we have the foundations, and the first one is there, an object, that which has shape, right? And what do we propose here? Well, we propose something different than the establishment, because we do propose objects versus concepts. And one of the biggest concepts that got us in trouble really was this little concept here known as the electromagnetic wave. And this was started really, took its form, right? The concept, right, took its form in the 19th century. We have two gentlemen there. One is Fresnel and the other one is Maxwell. And they came up with this thingy. But what you're staring at is not a thingy, because what you're staring at is a bunch of arrows, and those arrows are vectors. What is a vector? Magnitude and direction. It's a mathematical concept. So they're building this thingy with mathematical concepts, and obviously a wave, an electromagnetic wave, a transverse wave is not a thing. You cannot say that's the mediator of light. Not in science. You can do that in religion, but not in science. So they failed there. They described this thing. They said, look, it's a mathematical description. Yeah, but you can't use that as a thing. And you see all these people illustrating and sometimes putting it in motion where the electromagnetic wave travels. It's very scary stuff because they have a concept that is traveling. You have a bunch of vectors there, magnitude and direction, they're just numbers, and they're moving. All these numbers are moving, only after the 10th beer, And so what do? Well, we replace it with this. We replace it with the electromagnetic rope. We're saying that this is what they've been staring at without seeing for 200 years now. Okay, so we're saying we're replacing the electromagnetic wave with the electromagnetic rope. You can see why they got confused. They thought this thing vibrated, and they said, we don't understand what's there, but we can describe it with all these vectors. Yeah, all they had to do was replace it with a physical entity like we're doing there, putting a physical object, okay? And so here's our model for that. You have two atoms bound by that electromagnetic rope. They expand and contract doing their quantum jump, and by doing so, they torque the rope. And here it is. Okay, this is more or less what we're proposing. Everybody should be able to understand it just by looking, but we're giving you the explanation in the background. We're saying, look, the atom expands and contracts. By doing so, it torques the rope. Torsion is the fastest thing imaginable. That explains why light is so fast. Okay. So I think we're okay in everything. And another feature you can see there is amplitude. The rope has amplitude as well. So you have all the features. And here you have the model in static mode so that you can compare. You have the quantum model up at the top, and you can see what it is. You have this back and forth motion of the electron bead. For reasons that nobody knows, it jumps back and forth, right, between energy levels, which is a concept. Okay, so is the electron, by the way. The electron bead doesn't have any structure, okay, or at least no known structure, right? They only talk about its mass and its charge. And why does it fall? Why does it rise? I mean, the why question here is what compels it? What causes it to fall and rise? See, in our case, we have the shell, and it expands and contracts. So we can see why it occupies different, you can call it energy levels. But in their case, why does the electron bead fall? What attracts it? What's in contact with the bead? That's the question. Okay? And then you have this electromagnetic wave that comes out of the atom and goes one way off to nowhere. Okay? So all these waves, they just fly out and nobody cares where they go. And we don't have that. We have a rope. It's connecting any two atoms. When it expands and contracts, it triggers the other atom to react. Okay, so when you have an atom from the sun that's got high frequency, it touches an atom here on Earth, and then because of the high frequency, it stimulates it and forces it to go faster or pump faster. Okay, so that's when you get a suntan. At the bottom, we see something that, the rope already explains right off the bat, the speed of light, why it's constant. Yes, under the rope model, it's a constant. Why? Because you have a rope there and a certain length of rope, and you can torque it as much as you want. Doesn't matter. All you are going to get is the link lengths are going to be shorter, and you're going to have more links, which is, more links means frequency. Link length is the famous wavelength. So we can explain many features of our world with this model, okay, that quantum cannot explain whatsoever. Here's the construction. Okay, you can see it there. The thread turns, the construction of the atom, right? You have the electric thread and the magnetic thread. We just use those words simply because of convention, to keep with convention. We have the blue one there going through the center of the atom and builds the proton star. Okay? And the magnetic thread, arbitrarily again, no difference in color or anything. It goes around and encapsulates the proton star. And so there's our atom. You can see all the other ropes converging upon our atom from every atom in the universe. So that's the construction. The construction is made of the same threads that build the rope that interconnects any two atoms. So it's not like the rope is connected or attached in some way. It's part of the atom in the sense that it turns into the atom. Each thread builds the atom as well and continues on the other side to other atoms. Okay, so it's that's our model. and for light. And then obviously we have very briefly here, we have it for gravity as well. Okay, see if I can put it up here. If every atom in an astronaut is connected to every atom on Earth, you can see why the astronaut falls to Earth. Okay, so there you have it. That's acceleration of gravity. It accelerates because the ropes fan out. Okay, so we have an answer for the toe, the theory of everything. If you care to look at it as the gut. It's a little more than the gut, but the grand unified theory. We're uniting gravity with electromagnetism. And so, it's not an equation that's going to unite. It's going to be physics that's going to unite. And for physics, you need an object. The object is the rope. And the rope serves both for light as it does as well for gravity. And so here, once again, we have those are the foundations. You need the golden principle, which is you can't do physics without an object. An object is that which has shape. And so today, now that we have that introduction, that lengthy introduction, we're going to move to the distance and location. You know, those are two words also misconceived, misdefined throughout history. And today we're going to try to define them properly because those words are necessary to do physics. Not only do you need objects, but you need to define terms like, what is distance? What is location, right? What is space? Space is nothing, right? Synonym of nothing. And distance has something to do with space. It's that vacuum that's between any two objects, okay? And so let's get to it. Let's find out what all this stuff is, what these words mean in science, in physics, okay? Yeah, I covered almost everything. It's just a summary essentially. And again, people, their job is to try to tear my theory apart. Okay, first the assumptions. If you can destroy the assumptions, that's your job. In fact, I welcome any criticism of the assumption. People sometimes say, Bill, your assumptions or your definitions are irrational. And why? I mean, why are they irrational? And they never tell you. It's just their opinion. It's just, I don't like it. It's not what I was taught. It's not what my teacher taught me. It's not what is in the books. It's not what the physicists talk about, and so on. It's all authority, democracy, tradition. It's what's in the dictionary. I don't care what the dictionary. Dictionaries are all wrong when they're written by our ignorant forefathers. That we're creating a new language here. Okay, and so let's keep that in mind. We have a different language in this site. It's a language of physics for the first time in history, right? Nobody's defined these words in a rational manner. Okay, so let's move on to distance and location. And for that, we have to really, if we want to do it right, we have to go back to the Greeks. Good old Greeks, they gave us this, head start. They said, hey, here's our starting point. You guys take over. And they did a lousy job. That's the reality. And such a lousy job that no one has corrected them in the last 5,000 years. We still have the notions that the Greeks had, and they did a lousy job to begin with, so we ended up with a lousy job today. Why? Because we ended up with the mathematicians in charge of physics. Mathematics has no place in physics. Physics is explanation, mathematics is description. There should be no interference by mathematicians in physics. Physics that we do here with objects, not with equations. Even though I'm going to do a little bit of equations, show you that I have a tinge of mathematician in me. Okay, so let's start with the Greek schools here. And just to put it in the right context, here were some of the most famous Greek schools, right? Lasted couple of hundred years at least, right? And we're going to look at one specific one, and that's the one on the far left there. These fellows here on the left, they were from Elea, and they were the Eleatics, okay? And who were the Eleatics? Well, let's go with what they really believed in. We have their Parmenides. I think he was the father of the Eleatics, essentially. He was the founder. Then you had Zeno and Melissus, but they all had this idea that there is no motion in the universe. Yeah. Were they serious? Yeah, I mean, I can move my hand. What do you mean there's no, I can see it moving. And so they had this notion, they arrived at the notion that there is no such thing as motion, no such concept. Motion doesn't exist. That's essentially it. And here's Zeno. Aristotle covered him, and so did Plato. But Zeno, we have no written stuff from Zeno. We have only paraphrasing by Aristotle and Plato. Okay, and so here you have Zeno, and he's got these two famous paradoxes. And actually, he had several. He had like 19 paradoxes that have survived, but these are probably the two most important ones. The first one is the famous Achilles and tortoise. Tortoise has a head start, and in order for Achilles to catch up with the tortoise, he's got to cover half the distance first, and then half the distance from where the tortoise went afterwards, right? And then half the distance, so on. So they have all these infinite half distances, right? And so it turns out that according to Zeno, the Achilles never catches up with the tortoise, because mathematically, right? Because what happens is you always have to cover half the distance first. Okay, and what it is a play on distance and infinity. The fact that you can divide distance infinitely many times. This is where some of these infinities came into physics. They shouldn't have arrived there in physics at all. This is something related only to math, but they introduced it into physics. And what's the issue? Here you have Zeno. He explains it. He says the tortoise paradox, right? The competitors start running at the same time, and he says during this time the tortoise run 2 meters. It will take Achilles some further time to run that distance. Okay. In other words, he's explaining that as the tortoise moves, Achilles has to make up half the distance first. Okay, and so he never manages to catch up with the tortoise. And so essentially, this is a mathematical exercise that's got to do not with physics. It's got to do with something else. It's got to do with this, with lines. Okay, here we have the line. Okay, and what they're saying here is that a line is made of points. So you have a line segment, right? And we're going to chop it up into points. Well, how many points are in a line? Well, all mathematicians will tell you that there's infinite points, meaning there's infinite line segments within a line, okay? Because you can take any 2 points and draw a line. 2 points make a line, right? So since it's got infinite points between any 2 points, you always have a line segment. And because you always have line segments, right, you're going to have infinite segments. That's essentially what good old Zeno was saying. But what's the problem with this? The problem with this is that they're not talking about line segments. They're not talking about geometry. They're talking about itineraries. But see, they turn geometry into an itinerary discipline. It's got nothing to do with objects. It's got to do with how you unroll the measuring tape around an object, be it a cube or a ball or whatever. So what they're talking about really is lines and chopping up the line into segments. And that's why they say they have infinite segments. And that's the case of the distance. Now, on the bottom, you have the other guy, the guy who shoots the arrow. And Zeno was saying, the arrow doesn't move. You say, what do you mean the arrow doesn't move? It hit William Tell's son's apple. What do you mean it didn't move? So what happened just now? And so what they have there, this is now no longer on distance, but it's on time. It says time is made of moments or instants. Moment and instant is equal to 0 time, right? Because like a cross section of time. And so they concluded that if it's 0 time, the arrow is really not moving because it's occupying 0 time, the present. So where's the motion in the present? That was his rationale for this. So he concluded in both from the distance and from the arrow there, in both cases he concluded that there is no motion. No such thing as motion. Motion is an illusion. It's an optical illusion. There is no motion. And the only clarification I want to say up there is, you have the physics distance is just separation between the tortoise and Achilles, whereas the mathematical one is distance traveled. It's got nothing to do with the distance of physics, and that's where we find our biggest problem. Okay, and the Greeks never picked up on that because they were mathematicians. Plato said anyone who doesn't know geometry is not allowed to enter here. What was geometry? Math. It had nothing to do with things, with objects. What's a point? Point is zero-dimensional, right? That which has no part, Euclid said, right? So if that's which has no part, what kind of geometric figure is that? When he defined figure, same Euclid, as that which has boundaries. What kind of boundary does a zero-dimensional point have? And same with line. Line is one-dimensional. What are the boundaries of a one-dimensional whatever? So these are not geometric figures. The point is a location, and the line is an itinerary. So they're not talking about physics. They're talking about something else. Okay? They're talking about math, and they're going to describe with an equation the point and the line. That's what it was all about. And a fellow who came a few centuries later, his name was René Descartes, he came up with this. He wanted to know the position of a fly on the ceiling. I guess that's where he got his bright moment. And so he figured if he goes 4 steps to the right and 3 steps to the north, he arrives at where the fly is. So he came up with this Cartesian coordinate system. Okay, he published that in 1637, and this is what we use today. This is what everybody's being taught in high school, at least, right? If not in college. Okay, so these are known as Cartesian coordinates, and it allows us to locate things in space. They call it space. I don't know why they call it space. Space is not a thing. It's nothing. No, you have to locate it somewhere, and hopefully you locate it in a container of sorts, like inside a room or whatever. Okay, and then again, here's the let me skip this, otherwise we go too long. So how do we destroy all these notions? We got to get rid of Zeno and Descartes. We got to get rid of all of them because they're doing math, they're not doing physics. And so they got confused with all these notions. They said, look, we have distance, we can chop it into all these little segments. We're really talking about itineraries. Then the other one, you're talking about time. You say, well, it's made of moments of little segments of time, instants, right? And so the question is, what are they talking about? What are they talking about when they say a moment? What are you talking about when you say an instant? And we destroy it with the tool that I've invented. I recommend everybody use it. It's called the universal movie. Universal movie is every atom in the universe in a single frame. Okay, God takes a picture, and you have every atom at a given location. Every atom has distance with respect to all other atoms. Right? What is the location of one atom? It's a set of distances to all other atoms in the universe. Okay, very simple. And so in a single frame, all you can have is some of these static concepts such as object, distance, location, and existence. And you can see the word distance is up there. So what are these people talking about when they talk about distance? Well, they're referring to something else. They're referring to distance traveled. Okay. And when they talk about time, they're also talking about something else. They're talking about, moments. Here's distance traveled, okay, displacement. You can see it's on the opposite side of distance. The one on the bottom has to do with math, okay, and the one on the top has to do with physics. Distance is simply separation between objects, between atoms. Distance traveled, that's something the mathematicians do because they unroll the measuring tape and they want to know how far something is. So they're not talking about a fixed distance separation. They're talking about how much they have to unroll a measuring tape that has units that have been predefined. And that's in case of the distance. And again, here you have the one for time. You have moment, duration, and instant are at the bottom, together with time. They're on the far right. Okay. Why? Because you can chop up distance traveled, you can chop up moments, you can chop up instants, time as much as you want. You want to chop it infinitely many times, no problem. You will always end up with two frames for motion or for time. So this is where they failed. They failed because I can take, an instant. What is an instant? Instant requires two frames because it's time. And time is defined as at least two frames, right? You need two frames to conceptualize time or motion. So what these people never realized, they thought it was a cross section. But a cross section of time, a cross section of motion is called location. It's not called an instant. It's not called, a segment of distance. The itinerary, which is what Zeno was talking about. You can chop up as many times as you want. If you end up with either motion or time or any subcategory such as an instant or a moment, you have to have at least two frames. So I don't care how many times you chop up motion or time, you're always going to end up with two frames because the definition of motion and of time is two frames as a minimum. Okay, I hope we got that straight. On the other hand, separation, we can see separation in a single picture of the universal movie. We take a snapshot, there you have separation. So separation is different than distance traveled. Distance traveled is the one of math. So what's the problem? Well, you have, you say, is there a problem with this? Yeah, there is. Here you have good old Newton, who lived in the 16th and 17th century, right? And he came up with this. He came up with force equals mass times acceleration. And he came up with force equals mass divided by distance squared, which is the gravitational equation, right? So he's got these two relations, right? And one of the things that the mathematicians do today, they put one equal to the other. Like force equals mass times acceleration is equal to, and they start playing around with all these variables and constants and so on, right? We got a problem because these two are qualitatively different. They're not the same thing. The distance in the acceleration formula at the top, that's distance traveled. The distance in the one at the bottom, the distance squared, that's separation between two objects. Okay? Let me go over that in a second here, but here it is. We make a change to good old Newton. Okay? We say this is what's happening. Okay? We have, at the top we have force. But at the bottom, we have something different. Not force, but tension. What we have is a tug of war in a snapshot. We have weight. That's the W in the thing at the bottom there. You can see the little W's. That's weight. On the other hand, you have distance traveled in the top one. Okay? So we're talking about two different things. In the top, we have velocity, right? Which is obviously something in motion, right? And at the bottom, you have weight. And weight is a static concept. You have weight for any location in the universe. Okay, so weight is a static concept. And here, let me illustrate that. Okay, here you have an astronaut. Okay, who's falling to Earth, and you can see how the ropes fan out. Okay, at different frames of the film, right? So we have 3 different frames, and you can see what's happening. The ropes are fanning out. But we freeze the frame, and for that astronaut, we can just look at it as a single atom in his body, right? So all these ropes from the Earth are converging upon a single atom in his body, right? At a given location, because it's a static concept, that's the weight of that atom at that distance from the Earth. So weight is a static concept. We can conceptualize weight in a single frame. We can conceptualize weight simply by the number of ropes, effective ropes that converge upon that atom. Okay, so yes, weight is a static concept. Okay, it's not a dynamic concept, and people have this notion that it's a force, and no, it's a tension. Here you have the T for tension. Okay, so let's get it right. Newton had it wrong. Tension's not a force, by the way. Force means that someone does win the tug of war, whether you push or pull. Tension, everybody has a tied game. Nothing's moving. Tension is a static concept, and so is weight. Okay, so the distance in the bottom equation is not the little s, which is distance traveled in the upper equation. Okay? And another ridiculous thing that they have, and that's because it's math and not physics, is that they have velocity for a single point. Okay? They say, at this point, this was the velocity. And, so that's the speed at that point, except that speed doesn't have direction. Velocity has direction, but that's irrelevant here in a sense. First, because direction is a qualitative concept that belongs to physics. There is no such thing as direction in math. Okay? You're not going to put direction in an equation. What are you going to put, right? So what you have is velocity at a single point. But that's a problem because velocity is a segment. Velocity means something is moving. And so you say, well, how do they have velocity at a single point? I never understood that in high school. Then I figured it out. Yeah. What they're doing is cheating. They take the limit or whatever, and they say at that point you have such and such velocity, right? But see, velocity requires a segment. Okay? Velocity is motion. Motion requires two frames. You can't have a single frame for velocity. Math can get away with that, not physics. Okay, let's get that right. Okay, so this is part of the problem. Okay, so here we have the differences. We're going to compare distance versus distance traveled so you see the difference, okay? Here we have side by side. We have the force equals mass divided by distance squared, the gravitational formula on the left, and Newton's second law on the right. Okay, what are the differences? Distance is static in the one on the left. The other one is dynamic. Something is moving. You have an object that is moving. Okay, it's got velocity, right? That's the v. Okay, here you don't. You have static. You have a value of weight for a given location. So the distance is just separation. That's what that d in the denominator tells you. Distance is between two objects. The other one is the distance of one object traveling outwards, okay, from a given point, a reference point. Could be the same object itself, its starting point. Okay. Each frame in the movie depicts a static distance, whereas the other one is an itinerary, okay, a cross-section of an itinerary. That's what velocity is, cross-section of an itinerary. But again, if you have a cross-section of motion, infinitely cut motion, I don't care how much you cut it, it's going to end up with two frames because motion requires two frames. The velocity is motion, you need two frames. And distance decreases. You can see distance decreasing as one object approaches the other one. In the other case, the distance is increasing, okay, because you're unrolling the measuring tape, okay? And here you're just checking the separation. You don't care about the numbers, you don't care the units, you don't care how much. You just say, hey, the distance, the separation is decreasing. So you don't need to know how much. The other case, you need to know how much because you're going to be calculating, how much this thing traveled or whatever, how much time it took, whatever you're trying to calculate, but you're unrolling the measuring tape so the distance is increasing. And then the distance is towards the object that you're moving, and the other one is away from the object. It could be, again, the same object starting point. So you can see that the distance in the force, mass times acceleration, is different than the one for the gravitational equation. Okay, so now what is it we're doing? Well, that's what we're doing. We're unrolling the measuring tape. Okay, that's what math is doing. And so that's not the same thing as a separation between the two hands there. Separation there is just, we don't care how much. We're just saying there's so much separation. Here, there's less separation here, here. And, the closer you get your hands, you get less separation. We don't need to have a value. But when they unroll the measuring tape, they're doing math and not physics, okay? Because we don't care how much or what units. Mother Nature surely doesn't know anything about meters, okay? Okay, and here you can see that velocity and so on. You have all these definitions for speed, for duration, for velocity. They're all dynamic concepts. Weight is interesting because they don't have a definition. They have no idea what weight is after so many hundreds of years, okay? Says there is some variation debate as to the exact definition. This is out of the Wikipedia, by the way. Some standard textbooks define weight as a vector quantity. Others define weight as a scalar quantity. Yet others define it as a magnitude of the reaction force exerted on a body. Okay, so they have all these definitions for weight, and all the others are dynamic. So here we are, so many centuries later, nobody knows what weight is. So when they say, "What's your weight?" you say, "Well, I don't know, because I don't know what weight is." That's the answer. Okay, so here we have another issue which is troublesome, and keep this one in mind because it really is troublesome in physics. Okay, and here it is, that the fact that they equate this length with distance. Why? Because they're going to be measuring not distance, they're going to be measuring distance traveled, unrolling the measuring tape, the tip of the measuring tape. In the physical sciences and engineering, the word length is synonymous with distance. Absolutely. There's no difference in math between length and distance. Length is defined as straight line distance between 2 points. Length, the longest extent of anything as measured from end to end. And length is straight line segment, the distance between its endpoints. What they're doing is equating length with distance when these are qualitatively totally different in physics. In math, you can do whatever you want because all they're measuring is how many units. So they don't care if they measure length or measure distance. To them, it's the same because they're just going to give you a number, so many meters, so many yards or whatever, right? So they don't care what they're measuring. And for them, it's the same thing. And so, yeah, this is where we run into trouble because they're equating length with distance when they are qualitatively different. And here you have the definition from good old Wikipedia. It says length is a measure of what? Of distance. Absolutely not. Length is a quantity with dimension distance. With dimension distance? What the hell is the dimension known as distance? I never heard of it. I knew about length, width, and height, but now they have all this nonsense calling a dimension is a distance. So I don't know, you figure that out. It says length is commonly understood to mean the most extended dimension of a fixed object. No, I don't know if it's they're confusing measurement with the length, width, and height notion of length. Okay, so you can't confuse the two. There's two. They use the same word, and I think they get confused 90% of the time. Length, meaning measurement of distance, is different than length, width, and height, the length of physics. And this is what they're saying. It's the most extended dimension of a fixed object. No, length doesn't have any extension. Length, in other words, doesn't have any numbers. It's not the longest. All the length, width, and height are all of the same length because they're qualitative. We don't say, oh, the length here is longer than the width. No. Length, width, and height are just perpendicular straight lines. Right? Mutually perpendicular straight lines. That's all it is. So they have no length. Neither one of them. None of them. Okay. Various terms for length of a fixed object are used, and these include height. Okay. But here comes the big shocker. Okay. It says or vertical extent, width, breadth, and depth. Breadth and depth are not dimensions, but these people don't know the difference. And one of the things you should be aware of is that, like in Spanish or in German, right? Breadth and depth, breadth, especially breadth, does not have, there's no word for breadth. And breadth is a vector. Breadth means that you're moving, means the movement in sideways direction. That's what breadth is. Okay, and they don't have a word for that in Spanish or in German. That's so funny. I found out that a long time ago, that they don't have a word for it. They do have depth, and they do have elevation, which is the other vector. But breadth, depth, and elevation are vectors. They're not dimensions. These people don't know the difference between a dimension, a vector, or a coordinate. Why? Because for them, they're all number lines. They're number lines. They're not vectors. They're not dimensions. They're not nothing that we do in physics. They're all number lines. They're looking at the values. And so you have these incongruent definitions or notions that these people hold today. They talk about breadth when they should be talking about width, not breadth. And there at the bottom, I summarize it. Distance is what lies between lengths. Okay, what is it? Distance is the separation between objects, whereas length is the continuous matter that you find within an object from surface to surface. And so let me show you that here. Here's the rational version of all these words. Okay, distance, separation between two objects. Okay, length, continuous matter within the boundaries of an object. Okay, length is to matter what distance is to space. Okay, what is space? Nothing. That's distance. Nothing. Hopefully there's nothing there. Okay, even though under the rope model, the distance, ironically, is the length of the rope from atom to atom. I mean, if you're going to look at an object, you have a set of ropes, okay? But if you're looking at just two atoms, the distance between them is the length of the rope. That's so funny. But that's what it is. But then you have to put it in the right context, okay? Okay, and because of some all this nonsense, we end up with this individual. His name is Albert Einstein, good old Einie. And Einie came up with more ridiculous stuff. He wasn't really the one who came up with it, but they attributed to him, so I put him in there as the poster boy, okay? So don't laugh at me. There it is. And he came up with length contraction. Actually, it was, other people. But what is it? You have that little equation right there in the square root, and you see the little v there. The little v is velocity. That means the velocity of the object. As it approaches the velocity of light, which is the c squared on the bottom, you get 1, right? The closer v squared is to c squared, the more you have this 1, value that's almost 1. And if you have 1 minus 1, you have 0. And so the square root is undefined. That means this value is undefined. And that's what led Einstein and who knows who else to say that, you can't travel at the speed of light because you turn into what? Energy, whatever that is. Okay, but this is what we're talking about here. They talk about length contraction, but they're talking about distance contraction, meaning distance traveled contraction. They call it length contraction, but they're going to be measuring with the tape. They're saying, look, the measurer, the observer, the guy who's measuring, right, is going to measure at v equals 0. He's going to measure the ball somewhat, whatever value he's got there. But as the guy travels close to the speed of light, the observer, right, not the guy in his proper frame, because that guy doesn't see any difference, but the guy from far away who's measuring that, he's going to measure a contraction. It's Einstein's tongue contraction. That's what I call it, And so you have this contraction of the ball, but did the ball actually contract? And no, because it's an optical illusion, it means that the guy's going to measure something different than what is reality. So the ball did not contract. What they're saying is because in the proper frame, the guy doesn't see any difference. It's the guy from far away who measures, right, distance traveled, and he's going to measure the distance traveled from one edge of the ball to the other. He's going to unroll his measuring tape and measure distance traveled. And they call that length contraction. You figure it out now. So yeah, this is the problem. Language, and more language. You have to get the language straight. And here we have a different language, yes, but we have a rational language. They say, oh, but everybody talks this other language. Yeah, because they're talking nonsense. They're talking irrationality. Okay, so back to what I said before here. Distance, separation between two objects. Length, continuous matter within the boundaries of an object. I think it's straightforward. Distance is what lies between length. Length is the matter. What distance is to space. If God wants to have distance, if he wants to have location, really, he has to have distance with respect to every object in the universe. And here we see him once again, good old God. He's got to have distance to every object in the universe. Okay, then he has location. And if he has location, guess what? He has existence by definition, because exist means object that has location. God right there has distance to every atom. I hope those lines represent that, right? And so good old God not only has location, he finally has existence. We finally made poor old God exist. So please believe in God, because he exists. There you see him. Very clear, right? Okay. Anyways, with that.